switch there to weekly call.
Is the channel live?
Okay, I'm just testing the YouTube video. Then we'll get started. Hopefully, more people join. Adesh, can you speak?
Yeah, I can speak, but wait, I need to give
Okay, cool.
uh, roles to people who are joining in. Okay. It's like everyone can stream. Yes.
Right. Hello. You can hear me,
Yeah,
right?
yeah. Yes, sir.
Right. All right, let's start. Yeah. Hello, everyone. I'm Tanmay. I'm a mentee under Chipmunks along with Keval and Sadhna under our mentor Pranav. Welcome to our project, which is a simulation based hardware implementation of a chip 8 system using Verilog. So, what really is chip 8? When we started this project, we thought of it as an actual hardware 8-bit chip we can see and use, which is really not. It's actually an interpreted virtual machine of sorts, which has its own set of unique instructions being implemented on an external hardware system set to be running chip 8. So we can see chip 8 systems being implemented on various 8-bit microcomputers and systems like that. So why are we using chip 8? It's because that it doesn't take more than 4 kilobytes, and it's a very simple. It's very simple to run, and as mentioned, it can be implemented on fairly simpler microcomputers rather than having to deal with more complex architectures. And it also has a fairly simple instruction set with having not more than 33 instructions. And finally, another reason why is because it forms a solid foundation for us in learning more about digital design and also as a stepping stone for more complex projects using hardware description languages. So, speaking of hardware description languages, we are using Verilog as a hardware description language here. And what it means is that we are controlling the behavior of actual electronic systems and hardware and how we control the flow of data in them. And for this project, we are simulating the operations of a chip 8 system and how each of its modules interact with each other. To talk more about the architecture and mainly about the CPU module, I'll hand it over to Kevin.
Hello there. I'm Keval and I'm a maintain chipmunks. So this is our chip 8 architecture. It consists of CPU, memory, display and keypad. CPU is the module where everything will be executed, memory is where everything will be stored, and memory is 4 kilobytes large, and we have a display which is 64 into 32 pixels, and a keypad where you can give inputs. So basically we are displaying games on display and controlling via keypad that we'll implement. And then we also have a GUI wrapper. Since we are simulating this project, so we need a GUI wrapper to visualize the display. And now we will understand more about CPU. So as I said, CPU is main part of our computer. CPU is also a top module, and CPU operates on instructions. So CPU gets instructions which are 2 bytes long and 4 letters wide. CPU will execute based on those instructions only, and from getting the instruction to implementing it, CPU operates in 3 steps, which are fetch, decode, and execute. Each of these steps are implemented using a finite state machine, where a finite state machine is a small circuit that has a current state and changes to a next state depending on the inputs given to it, which we can understand from this diagram. So as I said, fetch, decode and execute. So the first step is fetch, where we have divided fetch into two parts, fetch 1 and fetch 2, then decode and execute. So here CPU operates under a clock which will provide a steady pulse, and the CPU acts on the rising edge of the pulse, that is 1, and CPU is stop acting when it is 0. So the fetch one will get the first byte of the instruction. Since the instruction will be 2 bytes long, so fetch one will get the first byte, then it will move to fetch 2, fetch 2 will get the second byte, it will move to decode, and then decode state will help the instruction to be understood by CPU using switch cases, and from there onwards CPU will execute the instruction and then go back to the original fetch state again. And whenever all of this is happening, it is simultaneously connecting to the memory and getting the data from the memory. But our memory is not part of our CPU. It's based outside of the CPU, and memory is 4 kilobytes long. And now let's talk about opcodes. So opcodes are instructions and opcodes are operation codes. So we have 33 opcodes in our chip 8 system, and in these opcodes we are implementing 4 letters in our opcodes, and the first letter of our opcode is usually a hex value, and in other 3 letters we can write a letter or a alphabet. So here n can be a letter or alphabet, and x and y are the locations of the registers that will be inside a CPU. So now let's talk about instruction 1NNN. So here 1NNN instruction is jump. So NNN is an address where our program counter will jump. So a program counter is an inbuilt register of CPU which will store the memory address of the instruction in a 12-bit hex value. And for this instruction, we have a small example 1356, where 356 represents the letters N and N, and the first byte of the instruction is 13, second byte of the instruction is 56. So the first byte of the instruction is stored on the address 200, other byte of the instruction is stored on address 201. Both of the instruction bytes are combined to an opcode, which is operation code, and then it will given to execute. So execute will execute that instruction using switch cases, and the first letter of our instruction it will use to find a perfect match for it for the execution. And for simulation and design, we are using Vivado, software by AMD, and where we can simulate it, design it. Also, we can actually implement on our hardware. So I will show you a demo of the CPU. So as you can see, we are loading our simulation here, and on the address 200, we have operation codes 13 and 56. So we have loaded the operation code here 1356, and our program counter changes to 356, and then from there onwards it will increment like this. And now for to talk about more memory, I'm handing over to Tanmay again.
Thanks, Keval. Hello again. I'm going to talk about the memory module. As we have mentioned, it has a total memory of about 4 kilobytes, which we are splitting mainly into two categories. We have our reserve memory, which doesn't take more than the first 512 bytes of the program, and the rest is for the program memory, which takes about 3.5 kilobytes. So we are reserving some interpreter code, which actually interprets our instructions in the reserve memory, as well as the font set, which is where we store our hard-coded characters, which will be again be used for our display or any other modules we need to use it for. So the program memory is where the actual magic happens. This is where our program code is stored. This is where it's executed. The fetching of opcodes, the loading and writing of data, the displaying of data, all that happens in the program memory. So we can also now let's talk about how we use the memory in the system. So we have our two main modules, which is our chip 8 CPU module and our chip 8 memory module. They of course communicate with each other here, and we can control the read and write operations in this system using our two signals, which we have called write enable and read enable. So if you want to write data to the system, that's when we know we have to turn write enable to high or set to 1. This is where the CPU will write data to a particular address in the memory. So it gets this address with the value of memory address out, and with the data which is in memory data out, it uses these two values to store whatever it wants to write to data exactly in the memory module. And using read enable, which is if that is set to high or set to 1, that is when we know the CPU has to read data from the memory module. This is where we can see it being used in the fetch instructions, as Keval mentioned. And this is where we are sending the data from the memory through memory data in, and the CPU can read that data. So uh, to next talk about the display module, I'll hand it over to Sadhna.
Thank you, Tanmay. I'm Sadhna, a mentee under Chipmunks, and I'll be explaining the display module. So think of the display module as a grid of pixels. So as mentioned, Chip 8 has a 64 by 32 display, which just means it has 64 rows and 32 columns, which is a total of 2048 pixels. So as mentioned by Tanmay, we know that Chip 8 has a very simple instruction set. So how that extends to the display is that our display is monochrome, as in each pixel can only have two states, which is on or off. So it's a monochrome display. So onto the working of the display. A key gate which describes the operation of a display is the XOR gate. And as you can see the truth table, it describes all the states that any pixel would have to take in a display. So the display could stay off, the pixel could stay off, it could be turned on, it could be turned off. And the final state is called a collision state when a pixel is already in an on state and the signal given to it is on again. In this case, the pixel gets erased as in it turns off. So next we'll describe graphics on a display. So graphics on a display is mainly due to sprites. So a sprite is a small graphical image or pattern with a maximum of 15 bytes. So what that means, to understand what that means, you'd have to understand the opcode used for drawing sprites, which is DXYN, where D stands for draw, X and Y are coordinates, and N describes the number of rows. So as we can see in the image, it's actually the image of an A. So in this, you see that it is 5 bytes long. Why is that? Is because each row is 8 bits. And since 8 bits is 1 byte, this is 5 bytes long. And all the ones are represented by the pixel turning off on, and the rest are all switched off. Next, we'll discuss the future scope of our project. But before doing so, we'd like to speak about how we went about this project. So, in the first week of our project, we started from ground zero. We learned what was Verilog, and we implemented some basic gates. And we also worked on a mini project assigned by our mentor in order to better get a handle on Verilog. And then we learned Vivado, which, as mentioned by Keval, is the software tool that we use to simulate our Verilog code. And then we learned about the FPGA design flow. FPGA stands for Field Programmable Gated Array, which is again just a hardware that you can use to design and test your Verilog code. And then we went on to learn about CPU, memory, and display module. And lastly, we implemented our top module, which coordinates all these three modules. A huge part of our TILDE project was to learn the core concepts of Chip8 and Verilog. And in order to further develop our project, we'd like to explore Verilator and Raylib, where Verilator is an open source Verilog and System Verilog compiler and simulator. This lets us mix Verilog simulation with other C++ open source libraries. And Raylib is again a C library for game development that we use to render graphics. With this, we can take the Verilator C++ simulation of a chip-8 core and use Raylib to render a display output in a window. Then we like to parameterize the design. So what that means is we would like to code the parameters in a Verilog module to be of easily adjustable sizes, constants, and other configurations without having to rewrite our code. This really helps us make our RTL code more reusable and scalable. Again, RTL stands for Register Transfer Level. It's just a level of abstraction that describes how data moves in our circuit. And lastly, we'd like to make our design more FPGA friendly. So, how we do that is by making our code more synthesizable. To synthesize the code it just means to make our circuit more easily convertible into a physical circuit. So that's it for our future scope. Thank you so much.
Thank you.
Any questions?
Hello, can you guys hear me?
Yeah.
Yes.
Yeah. Hello.
First of all, really great presentation, guys. It's a really cool project too. You guys did a good job.
Thank
I had
you.
one question. You guys mentioned that in the finite state machine of your processor, you have two fetch states. The first one fetches one byte, the second one fetches the next byte.
Right.
Yes, yes.
Why do you have two fetch states? Can you do this with a single fetch state as well?
Yeah. So
yes.
so we are getting the instruction from the memory, right? And in the memory, so we are reading only one line per one clock cycle. And in memory, we can only write 1 byte of instruction per line. So that's why we need actually 2 clock cycles. So for that 2 clock cycles, we are using fetch 1 and fetch 2.
Yep, that makes sense. That answers my question. Thank you.
Yep.
Thanks.
Akash, I think you can unmute.
Please try rejoining the the VC. It might help.
Yeah. Yeah, you should be able to unmute. Oh,
You guys have a demo?
Yeah, we have a demo for CPU and memory both.
That's awesome.
We have a simulation of what we have done in Xilinx Vivado.
Right. Are you able to get display output from that?
To have a display output, like we would have the simulations data would just show a bunch of binary codes, which will again, like if we have to access it through a display, we'll have to change it a bit to make it display the font set which we have used. And yeah, there's quite a bit of stuff, because if you want to actually implement it on a FPGA, we'll have to play a lot with timings. And like, if to give you an example, like to press a key press in a simulation, it would give it takes an instant basically, but in real life that would take a fair bit of time in terms of actually pressing a key press, the system understanding it. So so to play with that, we'll have to play with the timings, but that's definitely something we want to do with our project. So yeah, there's definitely a lot of future scope there. I saw a question by Shri Krishna. Yeah, so it's a simulation. We don't have a bitstream for it yet. Thing is, our actual code itself right now is not synthesizable. So that's what Keval mentioned there at the end. Sadhna mentioned there at the end. And yeah, so our current code is just for simulation. To have it synthesizable, currently it throws a lot of errors, but we can definitely, it is 100% synthesizable once we change a few things. Any other questions?
Yes, Akash will be asking the question. Let's just wait for that.
Right. I mean, if it's an issue, maybe like I'm fine with like typing the question. That's also fine.
Yep.
I can answer that.
Yeah, any other questions on text or on call?
I think Akash will be dropping one.
Yeah, Akash will be talking.
Yeah, I see Akash typing. Yeah. Yeah, no issues. We can read the chat, so you can drop the question then. Are there any questions on the YouTube chat or is it just here? Right. Thanks. Yeah.
Yeah, there are questions in the chat. Should I read them? Few questions from my end. Curious to know why 33 opcodes exist if 32 opcodes to give you 5 bits to use instead of now pushing the usage to 6 bits. Second, why use Verilator when Vivado provides you with perfectly, if not state-of-the-art, usable simulator? It works perfectly for the FPGAs that you are targeting.
Right.
For the second,
Yeah. Okay, we go.
okay. For the second question, why we will be using Verilator, because this is a simulation level based project where we want to simulate the display output, and in Vivado we cannot do that. So by using Verilator, we can make a GUI wrapper using C++ and Raylib, and then like that we can simulate the output of display real time.
A lot to do with convenience also. Like Verilator does provide a lot of convenience. Definitely, Vivado we definitely have to use when we have to actually implement it on FPGA. Yeah, 100%. But yeah, just for a GUI wrapper and using Raylib and stuff, Verilator does provide good convenience. And I'll also try to answer the first question. 33 opcodes is thing is like each opcode is actually, as we mentioned, like it's a combination of 2 byte instructions, and we are combining them. So it doesn't matter that if we have we are storing all the opcodes in our memory, and we can actually, the total number of instructions wouldn't matter because we have our we can handle those instructions uh, using various forgetting the word for switch cases. Yeah, so using switch cases, and as well as at the end of the day we are forming 16-bit instructions, and it's not an 8-bit instruction because we are using 2 different 8-bit bytes, and that is forming the instruction. So that is also a reason why we can handle more opcodes, and yeah, that is what is helping with our project. I hope I answered that. I probably could have answered that better. Mhm. Right. Yeah. Thanks. Yeah, we do have a lot more to learn. There's probably much more I could have said in that question itself. Sorry if I went wrong anywhere there. But yeah, thank you. Yeah, we'll also check out Whitus as you mentioned.
Yes.
I believe it comes with Vivado itself, Vivado and Whitus HLS. But yeah,
Naveen is
I think
asking, yeah, they have 8 bits, so just a design choice. No, um, it was how cheap it was made by the
yeah,
person
so
there.
it can handle 8 bits of data at a time. So we are fetching it separately. That's how we can. So an instruction is 16 bits because we are using two 8-bit um, 8-bit instructions. So that both of them together form one instruction. So yeah, right. Yeah, I'm sorry if we took too much time, but thanks for all the questions, everyone, and thank you so much for the wishes. So, and yeah, we'll hand over to the next team. Thank you so much.
Thank you.
Thank you.
All right, thank you, Chipmunks. That was a really good presentation. So, next team that's going to be presenting is the Bento team. So, Anit?
Yeah, just checking. Am I audible?
Yeah.
All right.
Roshni, go ahead.
Yeah. Good morning, everyone, and welcome to our presentation. We are team Bento.rs, and we're building a container runtime in Rust. Our mentors are Achyut, Alaina, Navneet, and Suchitra, and the mentees are Anish, Hemant, Manit, and me, Roshni. Anish wasn't able to be here today because of an emergency, but yeah, the rest of us are here. Okay, so let's start with what Bento is. So Bento is a lightweight tool that runs containers on Linux without needing special permissions or background services. So what is a container? A container is an isolated environment to run applications. So what a container does is it uses the same kernel as the host, thus making it extremely lightweight. You don't need to have your own host within the container. And it allows you to run isolated processes, that is independent of the processes running on the system itself. So it doesn't hinder with any processes. It also allows us to set up resource boundaries so that it doesn't hog up resources and affect processes within the system itself. And it has its own file systems, separate networks, etc. Then what is a container runtime? A container runtime prepares and manages the containers. So it is responsible for setting up the isolation environment. It starts the containerized process, runs the processes, applies the resource restrictions, and then it cleans up the container once everything is done. And a couple of, so what we're building is a low-level container runtime. That is, it builds up the containers from ground up and does all of the functions that I listed just now. And a couple of other examples are runc, containerd, and crun. So a couple of features that we are focusing on with this project is rootless. So what is rootless? Rootless means that you don't need host privileges to run the container. And this allows us to have a lot more security because you're not affecting any, by having host privileges, you're not having any issues. And because of this, the container can run without any external privileges on the system. And the second feature that we're focusing on is daemon. So a lot of processes require a daemon process to be running in the background to manage the processes. What our project has is a daemonless setup where each process doesn't have any background processes running. So the process starts up and then it executes and then it ends without having anything to maintain it. So redefining what Bento is. Bento is a container runtime that runs containers on Linux and is rootless and daemonless, and it is a low-level container. Over to Hemant to explain further.
Good morning, everyone. Okay, now that we have understood what a container is, let's see how containers actually stay isolated. This isolation is mainly built on two fundamental Linux kernel features, namespaces and C groups. First, namespaces separate a container namespaces separate what a container can see. They give each container its own isolated view of system. It's a set of processes, network interfaces, mount points, and even its own host name. From inside the container, it feels like it's running on a completely separate machine. Second, C groups or control groups. They limit and monitor resources usage like CPU, memory, network bandwidth, etc. This ensures that one container cannot hog all the system resources and affect other containers on the host. Next, let's talk about OCI specification. OCI stands for Open Container Initiative. It's basically a standard that defines how containers should be configured, started, and managed. The OCI has three specifications. They are the runtime spec, image spec, and the distribution spec. Since we are building a low-level runtime, we primarily focus on runtime spec. Now, the runtime spec defines how a container's lifecycle is managed. That is how a container is started, created, started, and stopped, and later cleared up on the host system. And it also relies on the concept of a container bundle. The bundle is a directory structure that contains everything that a runtime needs to start a container. It includes two key parts: a config.json file that holds all the container setting, and then it also has a rootfs, which is container's root file system. Moving forward to the config parsing. Now that I just said bundle contains config file and rootfs folder, the first thing a runtime does with a bundle is it passes the config.json file. We use a JSON. It's a Rust crate to deserialize or convert this config.json to straight into a struct that matches the OCI runtime spec. There are three important sections in that file. They are process, which defines the program to run, its environment variables, etc. Second is the root, which points to the container's root file system path. Third is the Linux, which contains namespaces configurations and C group resource limits. Once it is passed, we run a validation stage. We check if all the required fields are present. If something goes wrong during the passing or validation stage, we stop right there and we give clear error messages so that user can fix the bundle before even starting the container. Moving forward to rootless containers. Normally, running containers require root or sudo access, which can be a security risk. But with rootless container, we can run containers without needing the root privileges on the host. This is done using user namespace. In rootless containers, even if a process inside a container think it's running as a root, it's mapped to a regular user or an unprivileged user on the host system. Okay, this entire mapping is handled by the Linux kernel. This translation layer is what makes a rootless container safe. Even if a process escapes the container, it only has the privileges of a normal user on the host. Additionally, rootless containers act as a sandbox, isolating processes more securely and limiting their ability to affect the host. Moving forward to pseudo file system. After the initial setup of the container, we need to mount some essential pseudo file system inside the container environment. These include /proc, /sys, /dev, and /temp. Okay, these mounts provide critical runtime information that many applications expect in a standard Unix environment. For example, /proc exposes the process and kernel info, and /des directory shows the system and hardware details, and dev directory provides the device nodes and temp for temporary file system. And also from a security perspective, we can apply some special mount flags such as read only, no execute, or no set keys file system where applicable. This helps us to prevent unauthorized execution and privilege escalation inside the container. Over to Manat.
Right. So let's talk about this three process architecture which we are utilizing. So in this, we have three separate processes: the orchestrator, the bridge, and the init. The orchestrator mainly handles the orchestration of literally the entire thing. Meanwhile, the bridge is utilized to set up the namespaces and the isolation, while the init process is the actual container that has been created. So looking at this flowchart, the orchestrator initially forks to create your bridge process, and where the namespaces are all created and set up. Once that is done, you fork again to enter the init process, which basically is your final container, which then runs the container process. Meanwhile, the bridge, when it actually forks, it also sends this PID back to the orchestrator for later on starting this particular container. And once that is done, it exits. So this is how we basically do this using the double fork architecture. However, how is this rootless? So the fact of the matter is that to set up namespaces, except for the user namespace, all the other namespaces require some sort of uh, pseudo privileges, especially the capsys admin capability, due to which we need to first set up the user namespace, have that mapped within the container to root, but on the host as a particular normal user. And once that is done, only then we can, fork to inherit that particular init process as PID1 within the container. So this is the architecture, and we also utilize pipes for synchronization and sending the PIDs, and also for unprivileged namespace isolation. Now, this is a high level overview of the entire pipeline, which is the user provides the user bundle, that is the config.json, as well as the root fs. This config.json is passed, and then we create our isolated processes using the two forks system calls. We then set up the namespaces, the UID and GID mapping as well, which I'll explain further. We set up C groups to limit the resources the particular container can utilize or work with. And then within the container, we set up the remaining stuff and prepare and isolate its file system by setting up the mounts, as well as using pivot root so that it cannot see outside its current directory. And then we save the current state of this container within the state.json, and the container is then paused, and then it waits for the start command, and once that happens, only then it executes. So now for a little bit more detail, this is exactly what is happening. So when the user does bento create bundle and passes the bundle path along with the container name or container ID, the orchestrator process is basically set up. Now here we pass the CLI to obtain where the particular bundle is, and within that we pass the config.json. Once that is done, we create the pipes for the inter-process communication between the three processes which would be created. Then we fork the orchestrator process to create our bridge process, within which we then set up our user namespace. Now, the user namespace does not require any privileges, so that aligns with our rootless functionality. We then also use deny set groups to prevent the actual container from setting its own UID and GID mappings. Once that is done, it sends the ready signal to the orchestrator, which then handles the UID GID mapping with the kernel. Once that is done successfully, it sends back the map signal via the sync pipe, and the bridge is ready to bridge is basically mapped to root within the bridge process, but on the host system it is mapped to a normal user. So since it has all these privileges, then it goes to set the remaining namespaces, which is the PID namespace, the network namespace, and the Unix time sharing namespace. Once that is done, the bridge's job is more or less done. It just forks another time to actually create this container init, which inherits becomes the PID1 in this new PID namespace that was created. So once that is done, it also sends back this PID of the container init via the synchronization pipe, so that this can be used later on to start the actual container. And then the bridge exits. Then continuing from there, the orchestrator sets up the C groups or the resource limits that the container should lie within and utilize. Meanwhile, the container init undergoes the remaining setup, that is the pivot root, which basically ensures it cannot see outside the current root file system and assumes it is root. Then you mount the directories, the procs and dev as well as temp directories, which are crucial. Then you set host name and you set up the environment variables. Meanwhile, the orchestrator also, having received the PID from the bridge process, it creates the state.json file and it runs wait PID just to ensure the bridge terminates successfully. So once that is done, also the container init basically blocks on the read start pipe and pauses the container. So once that is completely done, the orchestrator exits successfully. And when the user runs bento start container with the container ID, it then writes to the start pipe to unblock this particular container, and then the container runs with the particular command which is defined in the config.json. So now let's look at our demo to make it more clear. So initially I run bento list to show that there are currently no containers running. I then create the first container, and these are a bunch of logs just to show what all is happening. Yeah, it's a bit heavy, but yeah. So you have your PIDs set up, then you have the inter-process communication that is happening, and the UID GID mapping is done successfully. Then creates the remaining namespaces, the init process, all of that stuff, and you can see the container test container has been created successfully. And to run it, you just write bento start test container. However, I go on to show that it has been created and its status is now shown over here. I then go on to create another few containers just to show that we can run multiple without requiring any background daemon running as well. And there you go. We have started three containers with the same bundle, and as of now, then we choose to start the test container. So the container is currently executing, and as you can see, I just open another terminal to show it is currently running. So yeah, and these are certain commands we have run within the container just to show that it is actually within the container. And these are all fields which were defined within the particular config.json, which was provided. So yeah, you can see the UID GID mapping, the namespace files, then the process tree, and the next part, which is just the mount parts. And then I opened config.json to show that it's actually not hard coded but actually defined. Yeah, so this was the massive thing. We ran the entire command, and you have your host name set there, bento test. You have your mount set up. You have your UID and GID mappings, which is basically more or less what all was there, and the namespaces info. So this was our demo, and yeah, that's about it. Now, what's next currently is that we want to integrate overlay FS, which is not particularly OCI compliant runtime spec or whatever. Like OCI compliant runtimes usually do not support overlay FS, so we are planning to add it as like a feature flag. And then we want to work on networking with Slurp4NetNS just to ensure you can communicate on your own network and stuff. Then also we've worked on seccom, but we haven't integrated it yet. So we want to do the seccom filtering to ensure that the particular container cannot make certain syscalls, and also integrate sudo terminal so that you can actually interact and run it clearly. And yeah, that's about it. Thank you. Any questions? Okay, yeah, I see a few questions. The non-requirement of privileges in user namespace you're using, it is Unix specific, because the thing is, for user namespace, it does not require any privileges per se, but all the remaining other ones require privileges.
Oh, okay, cool.
Okay. Since we're saving configs and states in JSON objects, what is, oh, this is a fair point. We didn't consider, yeah, the slower write as what you're saying. But the reason we utilize that is because it's well structured and easy to pass in comparison to other stuff. So that's why we used JSON. That was our main goal.
So you're doing a OS systems project, right? So in
Right.
systems, if you're using Rust to keep it fast, then this might introduce latency, was what I was thinking. I'm not exactly sure about
Mm,
this, but just
no, actually, okay. So yeah, okay, that's where I correct you. It doesn't introduce too much latency because we utilize this thing called JSON, which is a crate which doesn't read the entire thing completely. So it uses like I don't exactly know the exact thing, but what I do know is it's pretty fast and it doesn't load the entire file at a single point. So it ensures that only what is needed is done at a particular way. So yeah, that's why we even use JSON.
fair enough. As in reads should be fine because you're going to be parsing it using Rust itself, right? I was only
Yeah,
thinking about the write, but fair enough. Maybe
yeah.
we'll see if possible optimization.
Okay, yeah,
Also,
we'll look into that.
like creating namespaces and like mapping like files and stuff, the reading the JSON is probably very minimal.
Yes.
So one question, the reason the bridge process is there is to like minimize the amount of code that needs to run as root. Is that right?
Yeah, more or less. And also it was like at least what I know about the root containers like Docker's low level container runtime, it just skips all of this and sets up all the namespaces in one shot. So this
Right.
bridge process in essence would just become its init process because there's no issue there per se because it has all the privileges. Considering you run it with root privileges, this bridge is in essence was to do that. It was introduced to set up the isolation, and also since it's setting up this isolation and then later on setting up in this two-step process, it's not really inside the container as of yet. So it's like completely separated also. So the separation of concerns aspect as to why we use this separate thing. So yeah.
Yeah, definitely. And the user bundle, this is not an OCI image, is it?
No, yeah. So OCI image is for the high level runtimes like Docker per se. So
Right.
it works with that, and then that trickles down to the lower level runtime, which has the bundles within the runtime spec. So that's why we didn't touch the image aspect. Ideally, what our thing should do is upon being queried by like Docker's high level runtime, it should create the entire process and just hand over the current PID or whatever for a Docker to manage. Yeah, is what we aim to do. But as of now, it's working as a separate thing.
Got it.
Could you look into the question in chat also? I think
Yeah,
Pratham had asked a question.
Okay, I'm so sorry. Yeah.
Do you want me to read out the question?
Yeah, go ahead.
Okay. So Pratham had the question that he missed out on how we're handling file system bit. Are we using a hard-coded rootfs, or are we able to construct a rootfs based on layers obtained via Docker, save, etc., which would need overlay fs?
Okay. So to clarify on that aspect, there are two methods we actually utilized. One was using an already existing rootfs, and one was by actually manually creating this. So we did implement overlay fs, and thus the multiple layers which have to be finally converted into your merge layer, but we didn't integrate that, so we didn't put that in. However, we are able to construct a rootfs, and we just need to add it in like a feature flag or whatever. And in general, as far as I know, the low level container runtimes, they don't actually have their job is to not actually create the particular rootfs. Their entire job is to just set up the relevant stuff, which is why we're adding it as a separate feature flag, at least how it's defined in the OCI runtime. Did I answer your question?
Yeah.
Okay.
You mentioned seccomp for filtering syscalls earlier.
Yes.
Have you considered an approach like gvisor, as in like emulation?
Yeah. No, wait. No, we didn't consider that. We'll look into that because we were thinking of a simple. I mean, actually, we thought of one method which was using the BPF filter itself directly, which lists all the syscalls and literally just prevents any of the other syscalls being called. And another method we actually thought, Hemant, do you want to elaborate on that?
So we have implemented, there's a C library called libsecom. So we use that to call the BPF filters and create. So yes,
No, I was talking about the other idea, the
the
one which,
WASM.
yeah, the wasn't one.
The WASM, like we were actually trying to implement any new feature into this. We were trying to implement WASM as a JIT compilation, which is
Oh,
close to 50 to 100 times faster, they said. I read it in a blog. So, due to the time constraint, we thought we just need to only for to cover in this 5 weeks, we had to implement a simple SecCom filtering feature.
Right, that makes sense.
yeah. Were there any other questions? Oh, wait. Vinayak had a question. Config being specified as JSON is a spec requirement. Oh, no, wait. Sorry. It's not a question. Any other questions? Sorry. Uh,
Yeah,
okay.
you can
Thanks
answer
a
in
lot.
chat
All right.
and in the
Good
FAQ.
work, folks.
Okay.
Thank you so
That-
much.
Thank you.
Thank you.
Great work, guys. Okay, next up we have Webunner. So if we could have someone start presenting.
Just testing my mic. Can you guys hear me?
Yep. Also, Manit,
Okay,
please do mute your mic.
Oh, sorry about that.
You
Just
can
going
go
visible?
ahead.
Hello?
You are audible.
Yeah. So, hi guys, we are WebRunner, and this is our team. Our mentors are Achyut and Siddharth, and the mentees are Bhuvan, Satrish, Chiranjeevi, Ishan, Nishant, and Rehan. So, have you guys come across? So, almost all of us have come across website which can execute code on the web, right? Say, like when we learn stuff through W3 schools, or when we practice stuff through Lead Code, or even while working with others people on Google Colab and Replit, can essentially see that they are executing code on the web. Have you guys wondered how they have achieved that? So essentially, how do online code editors work? Most code emulators rely on a backend, and what that means is the moment the user enters code, types code, and hits execute, the code is sent to a separate system where the code executes, and the output and whatever other transactions have to happen between the package and the server. So, but this comes at a cost, and the problems with server-side execution are it's expensive, it's it has high latency and increased data load because like the transaction that has to occur between the platform and the server, and there are certain privacy concerns. So for like smaller projects and where there isn't enough funds to actually get server access, what if your online code editor didn't need a backend? That is, what if it could run completely on the user's system itself? So this is just a breakdown as to how browsers execute code. So the way modern browsers render web pages or render web games is they have JavaScript engines. So basically, like Chromium browsers have something called a V8 engine, which can render JavaScript and also support WebAssembly. And our approach was okay, for other languages, what if we could just compile them into WebAssembly, or what if we could just transpile them into JavaScript? And and use the JavaScript engine of the browser to execute code instead of relying on an external server. And that was our approach. So code can be executed completely on the client side, and we also get fast execution, privacy, and no server costs. So this is what you're building. Now that we found a possible solution, what we decided to build is we'll build a package that can support multiple languages, mainly Python, JavaScript, TypeScript, C++, C, and Java, where the developer can just use a package to execute code on the user side. And it is designed in such a way that it's lightweight, secure, and easily embeddable. So how do we run each language in the browser? Certainly for different languages, we had to come up with different approaches. So I'll hand it over to Ishant, who will explain how JavaScript and TypeScript are run.
Thanks, Rehan. Okay, so for JavaScript, okay, JavaScript. So browsers come with built-in JS engines, as Rehan just explained, like V8 and SpiderMonkey on Firefox. So we explored multiple ways for isolation and for good performance. So the first approach was iframes with content security policy. So with that, we would have script tags in the iframes running our code, and content security policy, so the code doesn't have access to things we don't want it, like network and stuff like that. And then the WASM approach would be to use QuickJS, which is a JS engine, which we would compile to WASM, and then the code would be executed in the bytecode that QuickJS forms. This would be safer, but as we'll see, this was much slower than the iframes. So we can see in our benchmarks that QuickJS approach took way longer in most cases. So we decided that we would go with the iframe plus CSP approach because it gives us a good balance of performance and security. So this is why we chose iframes with CSP. There's lower code execution time. There's no overhead for the engine, and it's easier communication. As you can see in the diagram, the iframe communicates with the executor package using post messages from the frame to the executor package, to the parent app basically. And yeah, that's how we decided on iframes with CSP. These were some of the milestones along the weeks. This was a playground we had just for JavaScript, and we tested some scripts with that, and we got STDN working with prompt and stuff like that. So TypeScript is just JS with static typing. So we would need to convert the TypeScript to JavaScript and then use the same executor that we had just talked about to execute that JavaScript. So for that, we used Babel, which is a JavaScript transpiler, and we bundled that with the package, so it would transpile the TypeScript to JavaScript and then use the same post message stuff between the iframes, the same executor to execute the JS. This was our TypeScript playground. You can see the TypeScript input is compiled to JavaScript. Then later we also have execution enabled. Now I'll hand it over to Chiranjeevi for Java.
All right. So basically, I'll be talking about Java. Now, jumping right into it. Think of this like a mini Java computer which runs right in your browser. So basically, you type your Java code, and then the browser kind of translates it into a language it understands. Basically, like try to imagine you are converting English into a secret code. Now, in technical terms, that's called compiling it into Java bytecode. This is something that that our machine can understand. That is stage one of our two-stage pipeline using TVM. All right. Now, what stage 2 does is that it takes that bytecode and turns it into WebAssembly. Now, what is WebAssembly that you might ask? It's basically it's like, you could say it's a really fast machine language for browsers. Okay, so that can help us run non JavaScript languages in the browser itself directly without requiring a server. Okay, just like that, after these two stages complete over, you hit run and and the code executes instantly, no server, no waiting, and you don't need to be online once all the site elements have been loaded. So the main integration thing is that we are going to integrate it as a sub package in our Webrunner mono repo. All right, so it fits seamlessly with the rest of the system. So that's pretty much it for Java. I'll be handing it over to Chatresh for. Oh yeah, wait, no. Can I have the next slide? Yes. Okay, so this is basically your milestones in Java. Over here, what's happening is you're gonna see the whole journey of what the user sees, like on the front end, and what the browser does. What the user sees is basically just they enter the raw Java code, they click submit, and they get the output. What the browser actually does is it has a whole step-by-step pipeline to to compile and execute your code seamlessly, and that's how the output is delivered into the front end. Next slide. Yeah, so I'll hand it over to Chatresh so he can talk about C and CPP, whatever. So he can talk about CPP progress so far.
So our initial approach for executing C and C++ in browser was using Wasmer, a universal WASM runtime. So this runtime supports file system and network. But so Wasmer had a already supported Clang in that runtime, but the problem with the Clang in Wasmer runtime was that it did not support libc++, which means um, the standard C++ libraries weren't supported, which means even simple functions like cout, cin wouldn't be supported. And it was slow because we had to load the runtime itself. It was a different runtime from the browser, and we had to load Clang on that and then execute it. So it took time and was slower. Next slide. Yeah. So then we came across Clang compiled to Wasm that would run on the runtime of the browser itself. We managed to find libc++ support to that. So this meant we could support both C and C++ on the browser along with file system. And we made a fully functional browser playground that supports both C and C++. We also handled basic user input and file handling. And this was faster than Wasmer runtime because it ran directly on the browser's runtime itself. And this is the playground. It runs both C and C++. Over to Bhuvan.
Thank you, Chatrish. Last in the line, we have Python, and we shall be discussing about how it has been implemented. So to give you guys a brief overview of the architecture and the execution pipeline involved in Python, our solution, makes use of a three-stage architecture. Firstly, we have the Pyodide setup. Pyodide is you could think of it as a runtime environment which has support to many of the Python libraries, and this helps us to compile Python code to WebAssembly. And the execution here takes place in two layers, the one which is the main thread and the one which is the hidden layer is the worker thread. The main thread is responsible for managing the UI. It sends codes from the UI and it fetches the results once it has been executed. The worker thread is the background thread which enables code execution behind the scenes, and this has been done to ensure that the UI which the user is currently on doesn't freeze and yeah, it keeps it responsive and smooth. Moving on, we have the execution pipeline. It happens in 5 steps. First, we have a request which is made to the PI executor, I mean the core module. The core module fetches the code from the UI and then makes a request to the PI executor. And the PI executor, on the other hand, initializes the web worker. Now, as I told, web worker is initialized so that the code can be executed on the background thread, and that is an isolated environment. So that's the second step there. Thirdly, in this isolated environment, we are going to load our pyodide, which will be compiling our code from Python to WASM, and then the code execution takes place within this isolated environment, and whatever the output is obtained will be redirected back to the UI using post message. Yeah, they could. Yeah. So talking about the interactivity and the packet management, we have made use of async functions, mainly to handle input operations, or in general, we have many blocking functions, and all of them have to be replaced with the ASIC counterpart using regex parsing. This is to ensure that the UI remains responsive and does not freeze it. And we have an automatic package import detection through PyPI, which is Python's package index, which enables the user to make use of Python libraries without explicitly mentioning them, and also to enable fast execution. Since Pyodide is a very quite resource intensive and heavy, we are gonna make use of something called package caching. This enables fast reuse in subsequent code runs where the the package remains in the runtime memory, and that can be reused again without having it to load it up again. So here we have some couple benchmarks with the performance by using web workers and package caching. Clearly on the left side, we could see that without making use of a web worker, the script execution takes place on the main thread, and throughout the execution process, the UI remains frozen for about 3000 milliseconds, which is about 3 seconds. Whereas with the usage of web worker, all the execution of the script takes place in the background, and that keeps the UI seamless. On the second, we have another set of benchmarks which talks about package caching. So when we run the code on basically the first time, we can see that pyodide loading takes about 7.25 seconds, whereas when we continue to execute code on the subsequent runs, clearly it makes use of lesser resources, and also the average time taken to execute code uh, is about 500 milliseconds. So that's there. So clearly it is quite optimal. Yeah. So over to Rihan now, who will be talking about packages and package structure.
So now that we have understood like how each language, how we approached our solutions for each language, it was important to assimilate it into all into one single package for the developer to use. So the first task was structuring the package. So we decided to use a PNPM monorepo organization, which is basically, if you can see on the right side, you can see that under the WebRunner package, multiple sub packages, that is core, PPP executor, and other language executors. So using PNPM workspaces, each language executor was built as an independent sub package, and the main advantages of this was it is modular. So even if one sub package needs to be worked on, it's not all in the same sub package, so it's easy to like stuff out. So while building, we were building like each one of them individually and modifying them to core, and it was quite easy to replace the code in Java without like tampering anything in C or JS. uh, that also makes it robust and maintainable. Another advantage of PNPM monorepo is that we can add more stuff, more language execution into this without messing with the main package itself. That leads us to the core package, to the core sub package, and it's essentially an interface between the web app using it and the language specific executor. We wanted this sub package to be there so that it's easy for the user to use it, and there's a standard format for executing code, handling the outputs, and also working with inputs. That is where the user sends the executor sends for the request for an input, and the user can send the input back, the value of the input back. So on the right, you can see how the flow is. Our main achievements with the core were it was a central bridge. It also had a standard communication pipeline and data format. So basically, what that means is communication pipeline. We had standard functions between the Webunner core and the web app. So like even if you're seeking input for say a Python execution, the user only had to handle work in a similar format, so the code base would be clean, enhancing robust nature. So another advantage with core was, like I explained in the previous part, different executors were having different sub packages, and in core we were essentially handling it all. So even if something broke or something needed to be changed, we could temporarily like switch off access to that certain executor while work was being done, and we could also add multiple languages on the project became bigger, as the project grew, and it handles routing, execution management, and error handling beautifully. So I'll hand over the mic to Nishant, who will explain the work we did with the playground.
Hello. Thank you, Rehan. So with this package developed, we basically, for the purpose of displaying, we created a playground that uses our package and gives a seamless and smooth coding experience in the browser. And we also managed to get file uploads downloads working for a few languages. Now we'll just show the demo.
So you guys can go and check the website out at this link. So let's run the execution for each language. Sorry.
So as you can see, accepting send inputs and handling the output and then showing it in the terminal pretty smoothly.
So as you guys can see, we actually imported the script from the local system instead of like actually typing everything out. And this was a massive milestone because this was to level functional, or else you'll have to copy your code everywhere and it'll be a mess. So this is the execution of Python, and yeah, it's working beautifully. So as of right now, C++, C, and Java are yet to be executed, are yet to be implemented because we were facing issues yesterday.
Java पता नहीं क्या बोले slow.
So some of our challenges and learnings were managing complex NPM and PNPM configurations, setting up the framework, handling duplicated packages and tooling, integrating WebAssembly-based compilers, working across packages. This was a major issue, especially while building. We faced a lot of errors, and debugging across multi-package setups. Thank you.
Yeah, any question?
Hey,
Guys, we are open to questions right now. So yeah.
yeah, I have a question. I think during the TypeScript explanation, you guys said that you're using an iframe, but later you guys used a worker thread. I was wondering why workers wouldn't work for a for the TypeScript pipeline as well. I'm sorry. Okay, maybe not TypeScript. Could you go back as a JavaScript? Yeah. So why couldn't this just be a worker?
So yeah, for while searching for the options for JavaScript, we did consider web workers. Then I believe like during testing, we were having issues while integrating all of it, all of the different packages. And also the main advantage with web workers is that it's faster, like it's more of a performance over security. So and it was difficult to like integrate CSP into that. So we are essentially using CSP to like block network communications, like preventing the user from going to fetching from random websites and stuff. uh, so in the reason it makes sense to use web workers in Python is because he has to load the pyodide WebAssembly compiler, which is a massive package. While for JavaScript, we are essentially still using the JavaScript engine, and the security was the primary concern, primary priority over performance.
However, the code is generated by the user and run by them as well. Is like CSP really a concern there? Since everything should be the user's intention, anyways.
Yeah, I mean, that's well, it depends on whether the user uses unsafe code, whether he runs unsafe code or not, right? Like, we can't expect that, but certainly while you're building a package, you wouldn't risk whether you wouldn't like want the user to be able to, on mistake, you do nonsense with it.
Fair enough.
Any other questions?
If you're running this for something like a lead code style like application, then the amount of time that it takes to run will also be a concern, right? So if you're running the code to the user's machine, then you won't really be able to get an accurate comparison between different users' code. So is this meant for that kind of use case, or is this a problem that you?
That's a good concern. Like, we didn't really think over. I think that's something you can look into.
I mean, mostly we wanted offline execution, but so that'll only be possible on the client side.
So I guess this, like, if you're running the code just for yourself, then this works perfectly well.
Anything else?
If there are no other questions, we can move on with the next team. Thank you, guys.
Thank you.
Thank you.
Yes, hello. I hope I'm audible. Yep.
Visible, I just need to check.
Yes, it's
Yes,
visible.
it is visible. Shall we begin?
Mhm.
Hello everyone. Audible?
Yes, yes, you are audible. Okay, I'm guessing we can begin then. Hello everyone. I hope it's been a pleasant day for everyone so far. I am Arjun, here with my friends Maya, Srivani, Tisya, and Vanshita. Our mentors being Vinayak, Hemant, and Mebin. We will be presenting to you our project, JamSesh. So, what exactly is JamSesh? I'll give you a situation. For example, you want to listen to music with your friends simultaneously, but the problem is you don't have a speaker. So they want to listen to it on their phone while you want to listen to it on yours, while you still want to have as little latency between both your devices. So now, how would you do this, right? Well, JamSesh is your savior. JamSesh enables real-time, low-latency audio streaming across multiple devices, built using WebRTC. So here's how it works. One device, it acts as a master and it streams audio to all the other devices. And the other devices, they can join as a client and they can connect and disconnect at any time. This way, all the devices hear music in perfect sync, or at least the goal being to have minimum latency. And this is irrespective of if the devices are in the same network or across the internet. So now let's take a look at what it uses. So it uses WebRTC, which stands for Web Real-Time Communication. WebRTC is basically an open source technology for real-time audio, video, and data exchange. So why do we use this? It's because it creates a direct connection between the two devices, and this helps in quicker data transfer, which means lesser latency.
All right, so let's take a look at the timeline of our project. We started with exploring WebRTC concepts so that we had a better idea of what we were working with. We next went ahead and got our public IP address from the Stun server. Next, we implemented a signaling server, which we will explain on later, and went on to implement a video call, a one-to-one video call. Again, why we did this will be explained later. Once we implemented the video call, we switched out the camera feed for device audio, and then we switched over to an architecture where we have one master streamer and multiple clients who can clients or guests who can join and listen to the stream. Next, we worked on improving audio quality, and Lastly, we are currently working on implementing room logic so that multiple groups can listen in without interfering with each other's streams.
Now, before we move forward, I would like you guys to know a few WebRTC terminologies. Starting off with the signaling service. As we can see here, a signaling server is dedicated to establish the initial connection between the two peers or two or more peers who would like to communicate. So once the connection has been established, you wouldn't need to use it for the ongoing communication. And it helps you to send a signal and yeah, that's how it goes. Then we have the SDPs or the session description protocols. These basically, once we know that someone has joined the conversation, we need to exchange the information about each other's systems that help us to establish the connection. So it includes the details about its belonging peers, for example, what agent it is using and what hardware does it support. So and then we have the ICE or the interactive connectivity establishments. These basically help us to figure out what are the best possible routes that we can establish a connection through. So it basically checks out every uh, route and whichever is the one that takes least time to traverse gives us the route. Then we have NAT, the network address translation. It basically hides your private device behind one public address and it helps you establish a connection between peer to peer, but it also acts as a blockage. We have 4 types of NATs. We have full core NAT, IP restricted NAT, port restricted NAT, and the symmetric NAT. Symmetric being the most restrictive NAT. The first 3 are simple NATs and they are easy to bypass using the stun servers, whereas symmetric NAT is complex and requires a more expensive server called the turn server to relay. Then we have the stun servers and the turn servers. As we can see in the image, browser asks a stun server what its public IP or port is in order to send that information to the other browser so that they can use that information to connect to each other. Stun servers are usually less expensive and they help you, they use a standardized set of methods including a network protocol for network translation and lets peer A and peer B connect when they're behind NATs. Then we have the turn servers or the traversal using delays around NAT. These step in when we have a symmetric NAT and they help to relay all the media directly from browser A to browser B using the turn servers. These are relatively more expensive than the stun servers.
Okay, so now that we have gotten to familiarize ourselves with the terminologies, let's see exactly how WebRTC works. So let's say you have two peers, peer A and peer B, and these two want to form a peer-to-peer connection with each other. So as we have seen before, initially it would require a signaling server. So the peer A would send an offer, SDP offer, from peer A to the peer B through the signaling server. And similarly, peer B will send back the answer to peer A through the signaling server. So the SDP offer or answer will contain the media information and all the information about the connection. There is no actual media transfer; it's just the information. And after this, the ICE candidates are being exchanged, which will give you the best possible path for the connection to take place. And after this, after the SDP offer and answer and the ICE frameworks have been ICE candidates have been exchanged, it would use the stun and turn servers to get the public IP address from each other. So after they have all the information about each other, they can form a peer connection and the media can be transferred through that connection. So after this, I think you have to go back to the previous slide. So after this, when we were getting started with our project, we started with getting our public IP from the Stun server just to get the feel of it. So we were able to get the IP address from the Stun server. We were able to bypass the NAT, and the Stun server was able to show our public IP address, and we were using ICE framework to collect this IP. After this, we were able to implement the signaling server. So first, we wrote our code and ran it locally, and then we hosted the server on Render, which is a platform to host websites and servers on cloud. So after this, after we set it up, we hosted it on Render. We were all able to communicate with each other and form a peer connection.
Right. So how did we proceed with JamSesh? So we first started off by implementing a simple video call service because the WebRTC video APIs are better documented and easier to work with. Another major reason was that the video call implementation basically acted as our blueprint for the project. So now we could focus on understanding signaling, peer connections, and real time streaming basics before we could tackle the harder parts. Once we got that working, we moved on to our main goal, which was capturing system wide audio from the client. Now, unlike browser mic capture, which is kind of simple, system audio capture is much more complex. So, more on that later. Next slide. So, let's talk about our journey from the video interface to an audio one. First, we set up a signaling server and then successfully ran a simple one-to-one video call locally. So here are two demos demonstrating our initial breakthrough. The first one corresponds to the signaling server being set up. Here Vanshita sends a message, hello world, over to Maya. And the previous slide. Yeah, and the second demo corresponds to the one-to-one video call between Maya and Vanshita. Comes the audio interface where we transition to system audio capture. Now, here there's a catch. Browsers don't let you capture only system audio, so there's no straightforward approach. The workaround here is to basically request both system video and audio via screen sharing. So now that we requested both streams, we just simply ignore the video part of it and then utilize just the audio track. So we first implemented this for single user streaming, or basically one-to-one, scaled it to allow multiple users to join. So basically creating a one-to-many streaming experience. The demo at the right is the one-to-many demo.
All right, so here are a few enhancements that we are implementing currently. So we have implemented improving audio quality using Opus codec, which is a framework through which you can control bitrate, and then implementing auto bitrate so that your the bitrate changes according to the strength of the network connections. Next is implementing room logic, which is currently in progress and we don't have a demo for it as of now. But the idea is that multiple groups of people can join without interfering with each other's streams. Next slide. Thank you. Any questions?
Could you drop a link to the demo? That's one of the questions.
Yeah, sure. So this video is one-to-many users. So in this one, we tested it out locally only, but yeah, this is the video.
Yes, so this is multiple users, but for testing purposes or to be able to show it in a demo, we just did it all in one system. But yes, it is on multiple users. Arjun says, hey JamSesh, had a small query. So you're requesting for access for both system audio and video, but you can't request for audio alone. Wouldn't it be very inefficient getting video if you're not using it? Okay, this is a good question, which even we were pretty stuck on for a while. But the thing is, here we aren't going to be using the audio. So, okay, the best way to explain this would be, imagine you want to buy apples. Okay, so what do? You go to a shop. So you go to the shop and you see they have apples and oranges. You're not going to buy the oranges, so you're not going to do anything with the video, right? So you're not taking it to the other. You're not taking it to your home, so you're taking only the apples. I hope that could clear your
Uh,
question.
So basically, while we are capturing the system audio and video, we're blocking the audio itself. So through the peer connection, there is no, or through the connection, there's no video actually being sent. It's only the audio that's being sent. So exactly, when we capture it itself, we're blocking it. So it wouldn't even be sent it. So the connection wouldn't the video wouldn't actually hinder the audio quality or anything. So next question is audio media is streamed across devices stored locally on main device. And I want to stream to Spotify. Yes, you can. You can do anything, any device audio is there. Let's say you're playing Spotify, you're playing a YouTube video or anything, or let's say even if you're like playing a game also, then you can literally stream that audio. You don't need to have, and it's not any local MP3 or something. It's the device audio. Like you're playing a YouTube video. You know how you screen share. So you screen share that video, but then what we're doing here is we're not getting any video. We're just doing the audio. So essentially, even when we are sharing, when we are starting, like when you click on share audio or something like that, it will show up the screen share pop up that you get where you have to choose your window or any tab that you want to share. So that's how it will be working. I hope that clears it up.
Okay, in the interest of time, we can take other questions offline. Yeah.
Okay.
Thank you for presenting. Next team.
Thank you.
And I have a bookmark of questions on the FAQ forum. You can add any points. Yeah, check out that too.
Am I audible? Okay. Yeah, 1 second. Okay. I hope the stream is available.
Am I audible? Hello.
Yes.
Yep.
So today we'll be presenting problem where the mentors are Anshul, Pranavjeet, Pranav, Yashmita, and Sai Jyoti, and the mentees are Anshul, me, Ayushi, Athar, Shashank, and Aditya. So students and researchers really need an AI assistant that's private, lightweight, and works fully offline. This is a problem that usual cloud-based tools really cannot solve. So we introduce problem. Problem is a study assistant that uses RAG or retrieval augmented generation alongside a large language model or an LLM to fetch and integrate trusted external sources during inference. By combining these capabilities, it produces answers that are accurate, relevant, and academically grounded. So, as you can see from the Venn diagram, problem basically sits at the crossroads of three big things. First, it keeps your data private and under your control. Second, it runs fast without high cost. And third, it actually gives answers which are backed by sources. So now let us look at the project architecture. It starts with a collection of documents. These documents are pre-processed and broken down into smaller chunks so that they're easier for the model to work with. These chunks are then passed through an embedding model, which converts both the chunks and any incoming user queries into a numeric form so that the system can easily understand it. The system then searches a special database called a vector DB to find the most relevant chunks of information that match the query. Then we use a hybrid search approach to capture both the exact matches and the contextual meaning. The retrieved results are then re-ranked to ensure the most relevant chunks are prioritized. This will be explained more in the further slides. So finally, the language model.
Yeah, the audio got cut off. One, if you could probably step in.
Um, 1 second. Yeah, she has an issue with the call, it seems. So yeah, after the data is retrieved, it's re-ranked to just see if we can get any, where if we're getting all the relevant chunks, and then the LLM generates the output based on that context. So for our first week, our team focused on getting a solid understanding of retrieval augmented generation or RAG. And we researched relevant papers and we've explored its applications in real world scenarios. We then analyzed the components of the RAG pipeline to see how they support in context learning. Throughout the week, we use GitHub to collaborate seamlessly and keep our workflows in sync.
Yeah. We started by breaking down documents into chunks of 200 to 500 words, making sure that complete ideas come together, and we also used an overlap of about 20 to 50 words. This is done to not lose context in between chunks. On the right, we see this is done to convert the documents, the knowledge base, into a simpler, easy to process kind of format. These are some chunking statistics. On at the top, we see the total count of chunks that an example.
Does he have technical difficulties? And
Hello, can you hear me?
Yes.
Okay. Okay, so these are some chunking statistics. At the top, we see the total amount of chunks that were generated, which is 2,434. We also see that the mean chunk on average had 153 words and 947 characters. At the bottom, we see that the biggest chunk had 407 words, 2,785 characters. These are just some statistics. We can go to the next slide. After we have our chunks, we need to actually convert them into a format that the computer can understand. We use an embedding model to convert each. This means that the chunks with related ideas will also be closer to each other in our vector space. The diagram on the right shows the relation between similar words and also opposite words, surprisingly. Man, woman are related, king, queen are related, and verb tense, it is smart enough to understand the relation between those two. We finally store these vector embeddings in a vector database. Here we've chosen ChromaDB because it is fast and efficient and allows us to quickly find the most relevant chunks later on. This is one such embedding that we have generated. This whole vector has n amount of dimensions, which we can set on our own. This represents one chunk, which is one complete thought.
Hello everyone, Shashank here. I'll be walking you through the progress we made on the retrieval part of a RAG pipeline and the CLI-based prototype we built. We focus on building the retrieval system using hybrid search. This approach combines two methods to find the most relevant information for a user's query. We use BM25 or best match 25 keyword search to find the exact word matches and rank documents by term frequency. This is preferred for specific or rare terms. Additionally, we use vector or semantic search, which understands the meaning behind the words, and it's better for handling vague or broad queries. Let us see the difference between the two search methods with a few examples. Suppose that a user asks, what are sorting algorithms? The BM25 keyword search finds documents with those exact keywords, sorting algorithms, successfully retrieving the chunk, introduction to various sorting algorithms, but missing techniques for ordering data efficiently because the keywords don't match exactly. But for a general query like how to arrange data, the vector or semantic search understands the meaning of the words and successfully retrieves
Hi guys, so my name is Aditya and I'll be talking about hello, hello. Yeah, can you hear me? Okay, so hi guys, my name is Aditya and I'll be talking about the optimizations and benchmarks that we implemented and generated for this project. I have a slight cold, so if you can't hear me, I'm really sorry. So GPU acceleration leverages the power of parallel processing, allowing multiple tasks to run simultaneously. This significantly speeds up the embedding generation and model inference, making it much faster than traditional CPU processing. By utilizing GPUs, even large and complex language models can be processed quickly and efficiently. This capacity is especially beneficial for handling large documents and managing heavy NLP workloads, where computation demands are very high. Overall, GPUs enable a scalable and efficient way to deliver NLP applications by drastically reducing the processing time. Chunking strategies. So why chunking? So LLMs often generate answers that are vague and unsatisfying because they might not receive the correct context that is organized well or is in full. To reduce these hallucination chances and to improve the quality of the response, we explored chunking, specifically semantic chunking. Semantic chunking works by breaking up documents into meaningful, self-contained sections that preserve the context and are coherent with the topic. This enables the model to retrieve more relevant information and produce answers that are clearer, accurate, and appropriate. So, inference, when we compared different chunking strategies, we found that recursive chunking was much faster to process, but it produced answers that didn't fully match the context. But on the other hand, semantic chunking took longer to process, but it was more consistent in giving answers that were relevant and accurate. So let's look at a few comparisons. When we look at recursive chunking, it works by splitting text using a fixed hierarchy of separators, starting from paragraphs, then sentences, and finally words. It breaks it down. This method is lightweight, fast, and doesn't require any inference, which makes it resource friendly, but it doesn't keep in mind the meaning of the text, which reduces the quality of the answer. Semantic chunking, on the other hand, splits the text based on meaning. It ensures that each chunk preserves its contextual relevance. This strengthens the quality and accuracy of the answers, but it comes at the cost of being slower, more intensive with resources, and it requires inference. Next slide. When we tested recursive chunking, the text was split into a total of 4,914 chunks with an average length of around 476 tokens. Smallest chunk was 362 tokens and the largest was 511. With semantic chunking, we ended up with only 2,869 chunks, where the average chunk length was 966 chunks. Shortest was 915, and the largest hit the 1,000 token limit. This difference highlights the trade-off. Recursive chunking creates more smaller chunks quickly, but semantic chunking produces fewer, larger, and more meaning-preserving chunks, which helps retain the context better for the LLM to process. So when we also, next slide. We also did a LLM benchmarking to understand which is the best model for our users. The key criteria that we were considering were the models needed to be small and compact enough, run efficiently on a wide range of devices, including older devices with limited resources. Actually, appropriate the answers are, and generation time, which reflects the speed. We tested multiple models in a single index document about operating systems. Next slide. Maintain consistency. This process helped us pinpoint the models that offer the optimal combination of speed, accuracy, and compatibility with older devices for our users. Next slide. For our benchmarking, we used a PDF document on OS and applied a prompt template to generate the answers to user queries. This image shows the different metrics we use to evaluate our LLMs. On the left, you can, next slide. Next. Yeah, on the left, you can see an answer generated by a model called Qwen3, 6 billion parameters. This is the response to the query, what is cloud computing, and explain in detail each of its types. So this is the format of the answer that we are able to generate. Next slide. The graph here displays the benchmarking results across multiple models. From our findings, we observed that for devices with slower or limited hardware, local models like Gemma 3 1 billion and Llama 3.2 1 billion performed much better, striking a really good balance between efficiency and answer quality. Thank you.
In this phase, our focus was on refining and optimizing our system for greater efficiency and accuracy. We started by improving the chunking process, which allowed for us to handle documents more efficiently. Then we enhanced the embedding retrieval process, leading to more accurate and relevant outputs. We also benchmarked multiple large language models and selected the one that delivered the best performance for our needs. On the development side, we took time to refactor our code. That is, we reorganized and cleaned up the internal structure of our existing code without changing its overall functionality. This made our code base easier to read, more maintainable, and better organized, which will help us develop faster and avoid future bugs. Finally, we packaged all the code to ensure smooth and efficient deployment. So now we will show you a live demo, and we do invite the viewers to suggest a question. So as you can see, this is our CLI for now. It shows up, it tells you if you have a GPU, and then it says that you can process documents. We are currently using the semantic chunking mode to help us get better answers. And for the sake of time, we've already uploaded 4 documents, 2 for the subject of operating systems, 2 for the subject of computer networks. And we've already processed this document. So if any viewer has suggestions for any prompts, we would love to see. A simple one would work best, maybe.
Could you show the source material again? What you
Yeah.
uploaded?
It's
Yeah.
PDF that. Zoom in a bit.
Zoom in.
It's fine. Just read out. Okay, that's the.
Yeah, so it's 2 PDFs based on operating systems and 2 PDFs based on computer networks subject.
Yeah, one question in the chat is the dining table problem. Dining philosophers.
Dining table.
Dining philosophers, yeah.
Okay. Yep. So this is the answer to your query. Dining philosophy problem is a classic synchronization problem in computer science, and this is how it produces most of the answers. We think that this prompt template is great. So if there's any other questions,
Can it take in follow-up questions?
if you have one, sure.
I don't have to think of something more complicated.
If you like, we can send you a video of the question being answered later on.
Oh yeah, another question is this local using what model maybe?
Yes. Well, we are using an API for this particular processing. We are using Grok. which helps us both process the data and retrieve it really quickly. So
Using this for fast inference. Otherwise,
yeah,
yeah, we can run local models as well.
for the sake of time, we just wanted the speed.
How are you guys doing the output? How is it
Output.
formatting so well?
I believe part of this is just the models output criteria output, but if where was it? I believe we added 10 here somewhere. We'll have to find that part and we'll get back to you. I don't remember which file it was in. So
Okay, another
we do.
question in the chat says, can you ask it about problem itself? If you can source your slide.
Can it source our own content? We haven't really given it our own content is. If we well we have something related to our slides as in the image processing. That's something that we'll have to work on. That's actually we're gonna come up. We actually had a slide after this demo to just talk about that, but for images it can't really process them right now. But yeah, the text it should be able to.
Is there any like mechanism to find what it is citing? So like, is there a way to check what chunk is making it say that?
I mean, we have this sources over here which says which PDF it's referring to and the pages that it is referring to.
Okay, all right.
There's a prompt in the chat. Can you put that in? It's a follow-up question.
I have to copy 1 second. Oh, I think it has a limit on it. Yeah, I think it has a limit on the input. We see several opportunities to expand and enhance our system. First, we plan to improve accessibility by developing a user-friendly graphical interface, making it easier for everyone to interact with our solution without needing technical expertise. Next, we aim to add support for cloud GPUs, giving users more flexibility and options for running intensive tasks without being limited by the local hardware. And finally, we will focus on further improving our processing capabilities, such as adding image processing to improve our system entirely by make it faster, more efficient, and capable of handling even larger data sets. And yeah, thank you for listening to us. If there's any question related to the project, we could answer them now. As for Adesh's prompt, I think we'll after our presentation is done, we'll add it and then we'll send it back to Adesh. The embedding model. I think Shashank will answer that.
Repeat the question.
He's asking for image heavy workflow. Does the model itself have the multimodal?
Okay, so for right now, we images are not processed right now. We for the scope we might use unstructured and OCR to build on it. We're not sending the images to a model right now. Does that answer the question? Yeah. Or even if it is a tabular, like data where it's not structured properly. I mean, comparison tables, concept maps. In such situations, we might use unstructured. Any other questions?
Oh, let's take any other questions offline. I'm guessing we can.
Okay. Yeah, we'll take them offline. Thank you guys for your time.
Thank you all.
Amazing work.
Um, Hello everyone. Myself Lalit, and this is EventLoop. So, starting with the mentors, we have Aditya Hegde, Akshaj, Nathan, and Tejas. Uh, Mentees, including myself and Samrid. Samrid won't be joining us due to some constraints. Uh, so, nonetheless, because most of an event. Sorry for the network issue. Hi, am I audible? Sorry. Yeah. So I was saying, as I was saying, this gets cumbersome, repetitive, and time-consuming for the volunteers. So to solve this, we present to you EventLoop. It is a one-stop solution for all your needs when getting started with an event, whether it is speeding up check-ins, reducing queues, and so on. Being a form builder, organizers can create their custom forms for each event. These forms can be filled by interested participants, and they will later get be presented with a QR code, which they can use to verify their identity at the venue. Through this, we hope to bring about more smoothness during events. So, as I mentioned in the previous slide, our key goals are to provide a form builder, which can be used to make custom forms and get registrations on one platform. Provide a quick and easy web interface to verify and permit participants. So that is using our QR codes, and
This we hope will reduce queues at the various checkpoints. So some of you, a lot of you might be familiar with the fact that is an existing project. It was already built by our mentors. So how this one differentiates from that is that we have integrated form builder functionality. We have also added the support for editing those forms. Um, Interested participants can also submit those forms. So the entire form builder functionality has been added in this version. We have also seamlessly integrated Google OAuth for creating accounts. There is effortless deployment using Vercel free tier. So all you have to do is clone the repo, create your account, and just connect your repo and the Vercel project, and that's all. You don't have to do anything else. You have to just set up the DB, the Couchbase Capella DB, and you're good to go. The current architecture is as such. So as I explained, the idea is that admin will only run a few commands here and there, and then once that is done, then the organizers can create various events and form builder, which will enable them to get registrations. After that, participants use the QR from the website to verify themselves at the checkpoints. So, going into a little more depth, this is how our sign up flow works. So, when a user signs up, we have our front end sending a request to Google OAuth. So once Google OAuth verifies the email session, it will return a credential response. This credential response contains JWT token along with some other details. We are particularly interested in only the credentials, the JWT token that Google OAuth provides us. This token, we send it over to our backend where we have another Google OAuth client. This Google OAuth client again verifies whether the JWT token is authentic or not. If if the JWT token is authentic, then it will send back the user details, and it will provide two tokens using which the user can access our site. So the front end, depending on the user role, whether he's a participant or an admin, it will serve different page layouts for according to that. So going in more depth about how the participant user flow works. So currently, as you saw, till this part we discussed in the last slide. So it sends the access tokens, and then participants can fill in registration forms. Once they submit that, it will be stored in the backend. So next, we have before we go into the QR generation, I'd like to take you through a demo. So here, as you can see, I've already logged in as an admin. So if I just go ahead and create an event, let's say it's a capture the flag event. Let's say it's on 15th August 2025. A single participant. So as you can see, the event has been created and there's a link to the form. So the idea is that when the events are advertised in the college, this link will also be shared along with that advertisement. So interested participants can access this link directly. So yeah, currently the form does not contain any fields aside from this one field comments. So if I just submit it here, sorry, there's some technical difficulty over there. But this is how this works. There is also a participant flow. So if I just log in with my participant account, So here you can see that it presents me with a QR code. If I were to scan this, I would my details would be verified, and the admins would know that I am a valid participant. So how do we generate the QR? We use the participants uniquely generated ID. How we generate that is using the email and the timestamp at which we are creating the ID. When we concatenate this with our secret key on the backend, we get a raw string which is unique and unpredictable. This we hash with the SHA-256 algorithm. Um, Once we have that, we encode it in base64 and send it back to the front end as an image. So here's the actual implementation. As you can see, we have the ID and the secret key. ID is referring to the email. ID is referring to this uniquely generated email, not the yeah. And then as you can see, it sends back the QR code. So how do we validate this QR code? So when the backend receives the QR hash, it queries the participant collection. So in our participant schema, we have a field where we store the QR hash. If there are any records which have this particular QR hash, we will compare those two QR hashes to ensure that the underlying secret key is the same. Once that uh, comparison is successful, we say that the user is verified and they can proceed to the venue. So what's the difference in speed? How much difference is it actually making? So in a typical scenario where you're manually checking it in your Google Form responses or in your Excel sheets, it would take anywhere between 5 to 10 seconds for any volunteer to check your details. But with EventLoop, all you have to do is scan a QR, and this reduces the time taken down to just 3 to 5 seconds. This difference becomes very significant when you multiply it with the number of people that you have whose details you need to verify at any given venue. So here we have a demo of how the QR scanning works. So as you can see, it gives you the name details such as name and email, and it tells you that the QR is authenticated. Um, Here, if I just pause it over here, you can see that this is the QR that was scanned. Yeah, and then when the backend sends a successful response, you get the um, response there. So over the course of the project, development of the project, I learned how JWT authentication works, how uh, HTTP only cookies are meant to be used in local versus production environments. Also, we used NoSQL databases, basically the Couchbase Capella database. So since I wasn't familiar with that, I had to start from the basics, understand how collections work, so on and so forth. Um, Also learned briefly about the Gen Web framework. This is a web framework based on Golang. Um, Also, to host this, we are using Versal serverless functions. Um, Learned how parameterized routes are created and handled both on the front end and the back end. And also, it was very interesting to see how QR codes actually work behind the scenes. So, future scope. There's a lot of potential with this project. Um, for example, we want to add live event dashboards, which would provide real-time updates about the events that are going on. Shortlisting views, which is basically like the form response tab that you have in Google Forms, except you also have the ability to shortlist people and reject people based on their form response. And participant logs. So let's say when I scan this QR, the admins should get a notification, or there should be a dashboard where they can see that this user entered the venue at so and so time. So that is the idea with the participant logs. Thank you, everyone. Feel free to post your questions in the channel.
Let's, there are some questions for you in chat.
Have you Okay, so Vignesh has a question. Have you tested the scenario if too many people try and scan the QR code, especially at MRD or the quadrangle? The network is basically non-existent. How do you guys handle this? Yeah. So we haven't done any bulk testing or load testing per se. We That is also one of the things that we wish to look into in our future scope. Using So we already have an infrastructure from Versal serverless free tier, which supposedly should be able to handle multiple concurrent requests. Yeah, that is something that we'll have to test out and see how it works out. So at least on the admin side, admin, organizer, volunteer, whatever, at least on their side, they would need an internet connection so that they can scan the participant QRs. But the participants themselves don't need a reliable internet connection. They can save the QR code as a screenshot, and they would be able to show that QR as well. But yeah, even when it comes to scanning the QR, you don't particularly need any heavy network bandwidth. Any 3G, 4G connection would be able to handle the QR scan. Also, the QR payload is pretty small. There's no, it doesn't have a huge payload. So yeah, yeah. Um, you could right click and just save it. You could just save the image, or we could have a download button over here, but it it's the same thing, same number of clicks. So yes, mailing QRs is no longer a thing, because the QR will always be present on the participant's home page. So whenever they go to this home page, um, whenever someone goes to the home page, they will have this QR, and also they can save it. So yeah, mailing QRs is not anymore in the code base.
Yeah. Any other questions? Not. Wrap up.
Philip, can you hear us? Philip?
Yeah, a lot of people have not even joined college, so this is one of their first projects. Really proud about that. Just something to showcase, talk about, even work on after the project's done. Yeah, one more thing in terms of future events, a lot more things will happen on our Discord, which is like open to the public, plus, yeah, recruitments as a club. Yeah, so looking forward to a lot of things in SEM workshops. We will try to stream them as soon as we can, so that everybody, even outside the club, or anybody in the world can join in. So, yeah. This year we have had like BCA people, EC people, third years, second years, first years, much more diverse from last year. Last year we had, well, we had a lot of projects, but they were all, yeah, within club members and around the same. Yep, much smaller crowd too. So yeah, set a new bar this year. If you have any project suggestions for the next year's guild, or um, any suggestions, and maybe PRs or feature requests, they are up on our GitHub right now. We will also be writing or asking our mentees to write a blog post around the technical implementation and more in depth than the slides. It will go up soon. And if you are in college or as a first year, it's an excellent opportunity to talk about your projects. We will try bringing up a road show or an expo where you can talk about these projects offline. That's it. Any other questions? Them up in chat. Yeah, feel free to like maybe have projects on your own, uh, work in like maybe teams of 2 or 3 on your own throughout the sem, and then maybe if you would like to present to your homebrew, um, yeah, if you're ready with a new project of sorts, you can give like a lightning talk on that. And a couple of the mentees from last year have become mentors. Yeah, that's also pretty cool. we encourage that. Yes, Bronze. His project was in the progress and then did not get completed. So this is his moment of truth. And considering like the first years here have not even started college, which means you're not in science and humanities, you're not in your department yet. Like even second years in that case. It's really cool. Learning Verilog for all of us. Yeah, maybe now we can ask. I mean, you guys can leave, or if you like to talk about anything, it's up to you guys. Maybe the mentees one by one. I see. We'll go in alphabetical order. Arjun. Anything, feedback or regards?
I mean, not much to say. It's been a wonderful experience, to be honest. I was really glad I decided to try this out. Thanks to my mentors Hemant, Mebin, and Vinayak, who did help us out throughout all of the weeks. Yes, that's about it. Thank you.
Who's next? Bhuvan. Chiranjeevi? Anybody, honestly. Otherwise, you can drop off.
I mean, I'll just speak off. I mean, I'm really glad I decided to participate. You know, the fact is that I registered for Tilde at the last moment when I was going through the WhatsApp chats, and I'm like, okay, maybe I don't want to miss out on the action, and thought, okay, let me give it a shot, and then just did everything last minute. Really glad I'm over here because it has been a wonderful experience working with people, making new connections. So yeah, overall, it's been an amazing experience, and I'm gonna thank all the mentors and the HSP members and everything for organizing this. Definitely looking forward to being here next year as well. So yeah, that.
Sure, I'll go next. Yeah, it's been great doing this project. Like doing this under Pranav. I'm studying in the same year as Pranav, and he was such a great mentor, and I learned honestly so much. It's I had registered for Tilde last year, also in the same project as Pranav, but yeah, I didn't turn out to do much after that. But right now, after doing this project, yeah, it's been great, and Pranav has been awesome teaching us along the way, and it's been also so cool to see like the second years doing so well with this, and like they have honestly done much more cooler stuff than I thought than I did, and yeah, it's been great working for this. So thanks HSP, and yeah, it's been a lot of fun.
Yeah, Keval, Lalit.
Oh yeah. When that tilde's message came, I was like, I will try and apply. And then I saw chipmunks, but then I asked some people, oh, what was it? It was Verilog. So I was super scared at first, but I just applied. I was like, there will be a lot of seniors and all. And yeah, I'll not probably get selected, but I got selected, and Pranav really taught us well, Verilog and everything. Yeah, it was great. Thank you, HSP. Thank you, Pranav. Thank you, all of the mentors and mentees. Yep.
Yeah. Next, Lalit, Nikhil. Shrivani, Vanshita. Cool.
Once again, congrats to all the mentees and any mentors here. Really, really cool job. Today was a great success. And yeah, hopefully, this is just the start, right? So, you please be active in the Homebrew Discord, build projects, maybe even mentor next time. There are many more opportunities. So yeah, congrats and thank you once again so much, all of y'all. And a huge thank you to the core, uh, Hector, especially Nathan, Anshul, all of y'all here, anyone if I'm missed. Really, really great job. The core has been, organizing them this like massively well. Yashmita, all of y'all. So, and the final review went super smooth. The whole program was amazing, despite some hiccups here and there, it went super well. So, congrats and thank you once again, core. Like, really amazing thing. Today was your first big event and it's a huge success. Hopefully, this continues. Yeah. Thank you to all of y'all involved here. It was awesome. That's it from my end. I think we can wrap up. It's already 1:30. Sorry for it being super late. Yeah. See you all soon, either in campus or online. Maybe we can host Discord VCs and so on. But yeah, thank you.
Bye bye.